Yep. Okay. So basically, this week, the focus is on structural geology, essentially. As usual, I have my notes here. If you'd like to scan it, you can follow along. I usually go quick, so if you want to have a look at anything properly, do that. Another little announcement: in the level 4 office of this building, you can pick up this stack of paper. It's been printed out now. This is your Geotech Design Bible, and you're gonna need to bring this into your finals 100%. Yeah, it's already been printed for you, but there's limited copies, so I would recommend going to grab it. They'll probably print more if students want more, but there's like an online version, but of course you can't bring that into your finals, right? So that's for the second half of the course. You want to grab that as soon as you finish this tute or in the break or something. Anyway, so yeah, just keep that in mind. Basically, I'm going to start by explaining a rock mass. This probably hasn't been covered, like, really, because I saw in the lecture notes, it's not until week 4 that they explain this, but the idea is that a rock mass, they have an analogy to a brick wall. So if you pretend that a rock mass is a brick wall, you have your bricks, and then you have the spaces between the bricks, like gaps, and that's essentially what like a rock mass is in real life as well. So you have your intact rock, and there's 2 words for this. It's either the intact rock or the rock substance. So if people are asking you to describe the rock substance, they're talking about, oh, that's like a igneous rock with these strength characteristics, etc., right? But for the gaps, those are called defects. And yeah, so defects are about the gaps in this potential wall, right? So we go over defects more like thoroughly next week, essentially. But defect mapping is a big part of what you're going to have to do out on the field for assignment part B. So yeah, just keep it in mind. But anyway, so that's just context. But this week is structural geology, right? And next week is defects, right? But there is some overlap in this, and it might not seem apparent. The idea is that structural geology is about large-scale structures formed by rock, and is due to the plate tectonic movement that we covered in week 1, essentially. So you'll see some examples of what makes structural geology forms and stuff later here. But next week, defects, that's about small-scale weaknesses in a rock mass. So that's where you're going more thoroughly in describing a joint or like a vein or something like that, right? Yeah, so that's the difference, right? Does anyone have questions about this, or is that okay? So the first type of feature that we're going to be talking about in structural geology is bedding planes. So bedding planes are exclusive to sedimentary rocks, firstly. So like sandstone would have bedding planes, shale would have bedding planes, stuff like that. Cross bedding. So in the bottom picture here, I've just got an example of cross bedding. That's where you have the layers running in different directions, like that. And you can imagine why this might form. It could just be a change in the environment. Like there could have been a river or something that ran through here before, and then it causes the sediments to set in a certain way. But most of the time, if there's not like these kind of external forces due to like the river or due to wind in these areas, bedding planes should be flat, right? Just setting due to gravity. Yep. And then you might want to consider the difference between the words bed and interbed, right? So the bed is about, these layers here are the beds, and then the bits which are like darker, obviously you can't see as far into the wall there because of the light, that's the interbed essentially, right? Yeah, and then there's a bit more details here. You can read through it yourself if you like. But yeah, there's different ways to describe your bedding planes. I'll explain this more after I explain the joint, but this is kind of diving forward into the defect mapping part of week 4, but it's really easy to mistake these two things because they're probably the two most common types of defect, the interbeds and the joints, right? But I'll tell you the difference in a bit. So I wish I brought my sponge. Basically, like rocks are ceramic material. If some of you guys might have done concrete, it behaves similarly to concrete in terms of it's very brittle, right? And so when you pull on it, you pull the rock apart, it can break due to tensile forces, right? Joints are essentially cracks, right? So they form a weakness in the rock, and that's significant because it might affect if you want to build like a structure or something on that rock, for example. And the other kind of force which you might see is like if the plate tectonics cause compressive forces, you'll see this kind of buckling effect, right? In this case, where you see these tensile stresses up the top, which cause joints as well, which again are just cracks, right? Yeah, so those are your two cases where you'll see joints essentially. Does anyone have questions about that? Okay. In terms of how joints are formed, how to identify joints firstly, and yeah, before we talk about bedding planes. So if you're out on the field essentially, right, and you're looking at a rock mass, and then you see bedding planes kind of like horizontally, those are bedding planes, right? Because they form in this kind of gravity, they have to form due to gravity, right? So they're going to be flat like that. Whereas joints, most of the time they form because of plate tectonic movement. So if I'm looking like down like this, you'll see joints kind of vertically oriented because they want to rip apart due to the plate movement, right? So yeah, it's about where you see these kind of defects, which might help you identify them, right? Yeah, so I've just included a few terms here that you might want to talk about. But again, this is a part of defect mapping next week. So yeah, the confusing thing is these two things I've talked about is a part of structural geology and is a part of defects, okay? But what we're focusing on for structural geology at the moment is the context, like how these things form, right? Whereas next week it's more about identifying the details of them, right? The next one is folds. So this one's due to compressive forces, right? So forms, yeah, essentially you have this buckling effect again, except you'll see this in rocks which exhibit a bit more ductility than your usual rock. So it could have clay minerals, micas. These things have a bit more ductile properties, these minerals. And so instead of just cracking like this to like relieve the stresses, you'll see that it forms this kind of warped shape, right? And that's essentially a fold. So here's an example. Oh yeah, and then there's like specific words to describe the points in these folds. So an anticline is like the top of this wave, and then syncline would be the bottom. So shale is an example of a sedimentary rock which has some clay minerals, so it's a bit ductile. It experiences these compressive forces, and then yeah, you'll see like the bedding planes being warped, and this is significant because when you have these bedding planes in conjunction with folding, right? Essentially, as the plates are moving, like the tectonic plates, these bedding planes are going to want to move at different rates. So they're going to be like kind of scraping off of each other, reducing its shear strength, essentially, right? As opposed to like a flat sedimentary layer, right, for a sedimentary rock, Those will kind of move at the same speed, but again, if they're folded, they scrape off of each other, reducing the shear strength. So yeah, keep that in mind. So therefore it's a weakness, right? Yeah, so domes and basins, right? These kind of look like folds in terms of it's got a wave kind of shape, but it's like got this center, it's like concentric, right? And these are caused by a few things. So for a dome, this is usually caused by magma uplift. So there's magma underneath the earth that wants to shoot up and like potentially form a dike, but it hasn't quite gotten there yet, and so it causes this shape to arise. The other one for a basin, right, which is essentially like a bowl shape. This is due to seismic activity. And subsidence. I got this information, by the way, from Googling it. So it's National Geographic said that. Yeah. To be honest, I don't fully understand the seismic activity. So if you want to have more of a read on that, you can read that yourself. But that's not the important part. I'm just explaining the context of how these things form. The important part is because of this shape, right? So for example, your dome, there's this magma uplift. It causes it to have this like upside down bowl shape. And then weathering and erosion causes the top layer maybe to be scraped off, so you're left with this kind of shape. What you're going to find is that you have your oldest rock here and your newest rock here. Let me just check I haven't gone the other way around. I'm pretty sure that's right. Bless you. Yeah, okay, so this is significant because basically, except for this exception, the idea of like, I think it's called stratigraphy, is that oldest rock is at the bottom usually, and newest rock is at the top, right? This is kind of the exception to the rule. When you have like these domes and basins, you might force the oldest rock to appear in the middle of this dome, for example. And the reverse is true for basins, right? Yeah. Any questions with that? Yeah, but that's the significance of, like, that's the most significant bit of information for domes and basins, basically. Okay, so unconformities, right? Yeah, so there's three types, and I really hate the naming convention for these because it's unconformities, and then the types are disconformities, nonconformities, and angular unconformities, right? And it just did my head in when I was trying to research this, right? But essentially, you want to focus on this bit of information. So essentially, for the first case, for disconformity, the bottom layer is a sedimentary rock of some sort. It's become eroded, weathered and eroded. So this is called an erosional boundary. You'll notice all of these have an erosional boundary, and these erosional boundaries are generally quite smooth because of just like water flowing. Yeah, it's just generally like ends up being quite smooth. So you're not going to have many jagged edges there. And then the top layer is another sedimentary rock. That's the definition of a disconformity. A nonconformity. I did that one in orange. A nonconformity is the bottom layer might be some sort of igneous or metamorphic rock, right? And then again, erosional boundary, and the top layer is this sedimentary rock. And then the last case is angular unconformity, where you have, again, sedimentary rocks, except something has happened in between these stages to cause the bottom layer to be tilted. And so I've got an example down the bottom. But for all of these cases, just keep in mind, the idea is that this unconformity, visually it's like very jarring, basically. It's a bunch of geology next to each other. It doesn't make any sense, but the idea is that there's a big time gap between all these things happening, right? That's what it's like. That's why it's significant, right? So for disconformity, yeah. So you have beds 1 and 2, for example, sedimentary rock. There's erosion that happens of some sort before beds 5, 6, 7 are deposited. These are just examples again. Granite, which is the igneous rock, was formed, and then that's eroded, and then the top beds are then formed. And then for angular unconformities, there's just an extra step where beds 1 to 6 become tilted. So there's a few reasons why this could happen. For example, the domes and basins, it could be due to magma uplift or something causes the tilting of the layers. Yeah, I don't know. Does anyone have questions? Okay. And the last one is faults, basically. So, yeah. Essentially, you just want to consider your plate tectonic movement again for this, but essentially it's a big fracture in the ground. And yeah, I don't know what else to say. Basically, the idea is that faults, by definition, just have to be a split in the rock. And so it can be as small as, what does it say here? If you whack a rock with a hammer, the cracks make faults, right? So that's a small scale fault. But if plate boundaries spanning thousands of kilometers are also split, that's also a fault, right? So faults is just a split in the rock of some sort. And then you basically have slipping that happens on these faults due to the plate tectonic movement. So you have your reverse, normal, and strike. So your normal case is tension with a fault, like with a piece of rock on either end of the fault are being pulled apart. And this is also called local lengthening, because if you visualize this diagram here, it lengthens the rock like horizontally, right? For your reverse slip, for compression, it shortens the rock, right? So there's local shortening happening. And then shearing, yeah, just shearing, right? So that's called a slip strike for that one. But yeah, anyway. So does anyone have any questions with that? Nope. Okay. I'm gonna do the quiz. So if everyone could just whip out their phones and scan this, we'll do this and then we'll dive into the workshop, right? All right, has everyone scanned that? Wait, should I wait till Sadia gets back? Okay. Should I wait?
I'm sure it's fine.
Okay, she can co-op with you later. Yeah, all good. I'm gonna get started, right? Let's pull up the music. Times 2 score for one question. a very good class accuracy. Yeah, okay, so next week's topic will be the describing intact rocks and defects. This week was just focusing on how everything formed. So yeah, I kind of trolled you guys a little bit. So basically, sedimentary rocks are the ones that have bedding planes. Foliated metamorphic rocks, they do look like this, right? But I'll tell you how they form. So if you went to the rock lab, right, you see foliated metamorphic rocks have these kind of stretched layers, but those aren't really due to sedimentary layers. What happens is that, so you have your local metamorphism and you have your regional, right? So for example, we have like some sort of magma here, and then we have maybe like sand. And then around the magma, right, you'll find that this was something like marble, and this was a quartzite, right? Those are examples of metamorphic rocks. But for your regional one, say we had something like shale, maybe something like schist, gneiss, right? So increasing levels of temperature, pressure, right? Whereas this one's only temperature, right? In this case, it goes up. But you'll find that marble and quartzite, despite being made from these sedimentary rocks with bedding layers, they're actually non-foliated, right? So the kind of so this is your foliated metamorphic rock, right? And non-foliated metamorphic rocks don't have a distinct kind of like layered pattern, right? And so basically the layers, you can't see layers for marble and you can't see layers for quartzite. So when it gets like heated up, it kind of all gets melted together, essentially, right? For your regional case, schist and gneiss actually are foliated, right? And it's due to like the layers stretching out as there's like an increase in pressure, right? So anyway, bedding planes aren't the same thing for those. You'll find the foliated rocks are formed due to a different reason, essentially, right? Okay. So essentially I'm just trying to help you guys here for assignment part B when you go and identify defects. Probably the two most common ones will be bedding layers because of the abundance of Hawkesbury sandstone in Sydney. You'll more than likely run into sandstone, basically, right? And so you'll see these bedding planes and you'll also see joints everywhere as well. So the joints will be the vertical ones, bedding planes will be the flat ones, essentially, right? So pure quartz sandstone doesn't really have ductile properties, so it would be pretty rare to see that folded, essentially, right? Whereas the ones with like clay minerals, in the case of shale, and then metamorphized clay minerals such as white mica in gneiss, these might exhibit some ductile properties when compressed. And then, is it pronounced nice or gneiss? I don't know. It's the one that's spelled like that. I think it's actually pronounced nice. Okay, anyway, which is not type of. This is kind of just a joke question. Anti-conformities are just that's not a thing, right? And here are your minerals. So, diamond's a mineral. There you go. All right, good job. Gatorade, yep. Coal's not a mineral. That one's a sedimentary organic rock. But yeah, good job. All right.